3-6 absolute value functions. So an absolute value function is written as f of x equaling a times the absolute value of x minus h plus k, where a, h, and k are constants, and f of x has to be greater than or equal to 0 for all values of x. A vertex is either the lowest point or the highest point of a function. And the parent function for an absolute value function is y equals absolute value of x, or f of x equaling x. And the vertex is at the origin, be 0, 0. So for absolute value functions of the form f of x equaling a times the absolute value of x minus h plus k, the vertex is h and k. Now you should recognize this format because that was very similar to a linear function, except for you didn't have the absolute value in there, you had a set of parentheses instead. But here with the vertex, you want to pay close attention to the h and your k because the vertex is the most important part of an absolute value function. Now the parent function, as we said, was f of x equaling absolute value of x. The type of graph is V-shaped, and that is very important because a quadratic would be f of x equaling x squared. Those are parabola shapes, so it's curved down here. So absolute value are V-shaped. So it is important how you have the vertex shown as a corner, like a V shape, or as a U shape for quadratic. The domain is all real numbers. I can put any x value in there and it will give me a y value. The range is all dependent on the lowest point or the highest point, the range. So it's all non-negative real numbers. Non-negative just because when you take the absolute value of that number for the parent function, it's always going to give you the positive form because absolute value means the distance from 0, which distance is always going to be a positive number. For example 1, use the table to graph f of x equaling 2 times the absolute value of x plus 1 plus 4. So they're giving us the values. We need to just put those in there. So they did everything for us. If I put -3 in for x, -3 plus 2 or plus 1 is -2. The absolute value of -2 is 2. 2 times 2 is 4. 4 plus 4 is 8. So they did all the work for us. We just need to plot these on our graph. So I go -3, positive 8, -2, 6, -1, 4, 0, 6, and 1, 8. You'll notice that it forms a V shape, and our vertex is right here. And on a table, that would be right here. And how can you identify the vertex from a table? Well, you'll notice that the numbers, the y values on each side repeat. When you do that, the one in the middle, the one that does not repeat, that would be your vertex. Next, use the table to graph this one. The table is already made for us. We just need to plot them down. So -1, -3, 1 and -2, 3, -1, 5, -2, and 7, -3. And we have our V shape here. It's just a little bit wider V. But that's what our absolute value function will look like for that example. Next, we're going to plot these. So we got -4, 0. So -4, 0 would be here. -3 and -1/2. So -3 and -1/2 would be here. -2, 1 would be here. -1, -1/2 here, and then 0, 0. So this one's a tighter one, but you can still see the V shape. You'll also know that if we were to put a line of symmetry through the vertex, they would be mirror images of each other. shape of the palace of peace and reconciliation can be modeled by f of x equaling the absolute value of x minus 31 plus 62, where x is the distance in meters from one side of the building and f of x is the height in meters. Graph the function and then find and interpret the key features of the graph in the context of the situation. First thing I gotta do is just label my axes. Now, since we are dealing with length, we can only use our quadrant 1 because we can use positive numbers. So I'm going to count by tens. So 10, 20, 30, 40, 50, 60, and then this one will be 70. Down here, 10, 20, 30, 40, 50, 60, and then 70. I'm going to create a table of values here. Now, one way to create your table of values is if you grab your calculator, go to the y equals, and we're going to type in this equation. So I would have -2. And then if I hit the math button and go over to numbers where it says ABS, that's absolute value, and choose that one. And then I just put x minus 31 and parentheses and then plus 62. I could actually graph that here. You would see part of my graph there. But let's go to our table of values. So second graph gives me a table of values. And let me just go back to make sure that I have everything in here correctly. Okay, so second graph. Now I'm going to scroll down a little bit on here. To find out where the highest point would be, because that's going to be my vertex. And it looks like 62. If I keep going down, so 3162 would be one of the numbers I'm going to use. So if I come here, 3162, I know I can have a 0, 0. That would be an easy one to plot on here. Now let's see when x is 0, when can we get, or when y is 0, and get to another one. So 62 is 0. So when y is 0, x is 62, so I can have 0 here and 62 here. And then I'm just going to choose some other points in there, and I will just choose another one where y is 30. So now if I come back to my calculator, when y is 30, scroll up. Here I have 47, so I can put 47 here, and then go back to here, find another time when it hits 30. Now I could have just done 60 and 60 as well. That's up to you which numbers you want to use. But now if I were to plot these, 0, 0, I would have 0 and 62. It could be here, or 62, 0. Then we have 3162. So 3162, that's roughly here. And typically I only need 3 points, and one has to be the vertex, which I do have there. So now I'm just going to draw my line now. That's what my graph will look like. Now on a calculator, if I wanted to graph that, I would just need to change my window settings to make this a little bit easier. So the x minimum is 0, the maximum, I'm going to make that 70. Scale, we can count by tens. The minimum is 0, the maximum, we'll go 70 here, counting by tens. Now if I were to graph this, you can see our graph there. Now the next thing we need to do is interpret the key features of the graph. So on this next slide, I have our graph listed here, which is similar to what we drew, and we need to identify the vertex. And the vertex we said was 3162. And we need to interpret what does that mean. So that means the maximum height of the building is 62 meters when the distance from one side is 31 meters. So max height of 62 meters when you're 31 meters from one side of the building. The intercepts, so where is it across the x-axis and where is it across the y-axis? Well, we know the intercepts are 0, 0, and we have 62, 0. So what does that mean? It means that at 0 meters and 62 meters from one side of the building, the height is 0 meters. So the height of building is 0 meters at 0 and 62 meters from one side of the building. Okay, so this would be one side of the building, this is the other side of the building. Next, the domain and range. The domain, all the possible x values, you can see that it's between 0 and 62. So the domain would be x such that x has to be less than or equal to 62, but greater than or equal to 0. And the range, y such that y has to be greater than or equal to 0, but less than or equal to 62. And then the relative distance we would have, it just means it can't be, can't have negative values in here. So this would be, it just be all heights greater than 0, but less than 62. And then the positive and negative parts, when is it positive, when is it above the x-axis, and when is it below the x-axis? That's all based on the intercepts. So it's positive when x is greater than 0, but less than 62. And the negative, though the height of the building can never be negative, so we're not going to worry about the negative. Next part, increasing and decreasing. When is it increasing? So it increases when x is greater than or less than 31, but greater than 0. And it decreases when x is greater than 31, but less than 62. Next part, we have symmetry. So is there any symmetry? Well, we can draw a line of symmetry through here, and that would be x equaling 31. And what does that mean? That means the height of the building is the same on each side of 31 meters from the end of the building. And then our last part is dealing with, a couple last parts is our end behavior. So the end behavior, you can see that it's all pointing downward. So we could say as x increases or decreases and decreases, our y decreases. And the relevancy of the end behavior doesn't impact meaning of the problem, because that wouldn't make sense that you would go down to the negatives when you're dealing with height of a building. Next example, the roof. The shape of the roof of a barn can be modeled by f of x equaling negative half x, or negative half times absolute value of x minus 20 plus 10, where x is the distance in feet from one base of the roof, and f of x is the height in feet. Graph the function, find and interpret the key features of the graph in the context of the situation. We're going to do something very similar to what we just did. This time though, we're just going to identify the key features. So the first thing we're going to do is we're going to use our calculator to create the table of values. So we grab our calculator, go to the y equals. So we need negative 0.5, so half is 0.5. Hit the math button, go over to numbers for absolute value. Then we have x minus 20, then parentheses, and then plus 10. Now if I hit graph, again, you can see what the barn would look like, or the roof of the barn would look like. We could keep it as that, that's fine. Second graph will show us a table of values. We want to just find the highest point, which it looks like it's the highest point is 10. So if I just use integers, I can use 2010, 22.9, 18.9. Let's see, we'll use 2010. We'll use 0, 0. And on the other side, we would use 40, 0. Again, we can count by tens here. 10, 20, 30, 40, 50. These are 10, 20, 30, 40, 50, 60, 70. We have a point at 0, 0. We have a point at 0, 40. We have the high point at 2010. And so now we can draw our graph. And now we have enough to answer the questions. We're just going to identify the vertex here. The vertex is going to be 2010. Well, what does that mean? It just means when you are 20 feet from the edge of the building, the highest point of the roof is at 10. The intercepts, where is it across the x-axis? We have 0, 0, and we also have 40, 0. That means the height of the roof from the peak to the edges are 0 when you're at one end of the building, and then you're at 40 feet from the other side. Next, the domain and range. So the domain, we got x such that x has to be less than or equal to 40, but greater than or equal to 0. And all I'm doing is just using the edges here for my x variables. The range, y such that y, and here I'm just using the highest and then the lowest point. So y has to be less than or equal to 10, but greater than or equal to 0. Positive and negative, it's always positive. And here, the negative wouldn't make sense because you wouldn't have the height, you can't have a negative height on that. So positive, it's positive when x is greater than 0, but less than 40. Moving on to the next key features, we have increasing and decreasing. So it's increasing when x is greater than or equal to 0, or less than, when x is greater than or equal to 0, but less than or equal to 20. And then it's decreasing when it's greater than or equal to 20, but less than or equal to 40. Now it's, yeah. Next, we got symmetry, drawing our line of symmetry. So this would be x equaling 20, which just means that when you are 20 feet, if you're whatever side you are from 20 feet from the edge of the building, you're going to be the same height on each end of 20. Next, the end behavior as x increases and when it decreases, your y decreases. Now, there is no relative meaning to this one because you cannot have negative values here. The end behavior, everything would all be positive in this case. Moving on to the second part, translations of absolute value functions. When a constant is added to x after the absolute value is evaluated, the result is a vertical translation. It just means it's moving up. Or if it's a negative number, if it's subtracting, then it's a vertical translation going down. So just like when we went through that before with linear functions, when k is greater than 1, it goes up. When k is negative, it goes down. Likewise, with h, you have horizontal translations when a constant is subtracted from the x or it's added from the x on both sides. So when h is greater than 0, you move to the right. When h is negative, you go to the left. Again, to help you with this, all I would do is take x minus h and make that equal to 0 and solve for x. So here I would add h to both sides. So when x is positive, I go to the right. Let's take a look at an example. It says describe the translation in j of x equaling the absolute value of x minus 4 as it relates to the parent function. And the parent function is f of x equaling the absolute value of x. The blue graph in the picture here is the parent function. You can see that it moved the vertex, and I'm looking mainly at the vertex, it moved 4 steps to the right. So this would be right 4. Now, if you didn't have the graph itself, how could you determine that? Well, if I take what's in the absolute value, x minus 4, and make that equal to 0, because the parent function, the vertex, is at 0. If I add 4 to both sides, you can see that x equaling 4. So that means I moved 4 to the right of 0. Next, we have x equaling absolute value of x, and then I subtract 8 afterwards as it relates to the parent function. So this is our k, and since the k is minus 8, this is going down 8. So I'm just taking the whole function and just moving it down 8. I'm moving the vertex down 8. Next, I have x minus 1.3. Describe the translation. This is in the absolute value, so I take x minus 1.3, set it equal to 0, and solve for x. So I have add 1.3, and I have x equaling 1.3. That means I go to the right. 1.3. Describe the translation here. Here I have multiple translations. If I go from blue to the red one, it goes to the right 1, 2, and then it goes up 1, 2, 3. How do we get that? Here's your 2 to the right, here's your 3 up. So right 3, or right 2, I mean, and then up 3. Everything else stayed the same. Next, describe the translation here. Again, my vertex is at negative 1, 6. How do I know that's negative 1? Because if I do x plus 1 equals 0, subtract 1, I have x equaling negative 1. So it went to the left 1, and then this plus 6 means it went up 6. Everything else would stay the same. Next, describe the translation in R of x equaling x plus 2, and then I subtract 4 at the end. So again, x plus 2 equaling 0, I subtract 2, x equaling a negative 2, so that means I go left 2, and then this minus 4 means I go down 4. And we also have dilations, which means you have stretches and you have compressions, in both horizontally and vertically. So multiplying a constant a after evaluating an absolute value function creates a vertical change, either a stretch or a compression. So if the absolute value of a is greater than 1, and the a is on the outside of the absolute value, then it's vertical, and it's a vertical stretch. Now, if the a is on the outside of the absolute value and a is between 0 and 1, then it's a compression vertically. Likewise, if the a is inside the absolute value, when it's greater than 1, then it's compressed horizontally. And then when it's inside the absolute value and it's greater or less than or equal less than 1 but greater than 0, so if it's a fraction less than 1, it's a stretch horizontally. Now let's take a look at some examples. Describe the dilation in each of the functions as relates to the graph of the parent function. So here they're telling us the graph, showing us the graph here. But if I look at the equation, 5/2 is on the outside. So that means this is a vertical dilation. So just keep in mind when it's outside, this is vertical. When it's on the inside, then it's horizontal. Now vertical, then you take the factor of 5/2. The absolute value of 5/2 is 5/2, which is 2.5, which is greater than 1. That means this is a vertical stretch. That means if I take this blue and I stretch it vertically, it's going to now look like the purple one. It makes it more steep. This is a vertical stretch. Letter B, you see the 2 is on the inside, so this is horizontal. And the absolute value of 2 is 2, and 2 is greater than 1. Since this is a horizontal, that means I am compressing it horizontally. So I can only move it horizontally, so I'm pressing it in. So I'm taking the blue and moving it in. It makes the purple, or the red here, more steep. Next, match each description of the dilation with its equation. So vertically. So vertically means it has to be on the outside. So that means we got this one and this one there on the outside. A stretch vertically means the A is bigger than 1. So this one's bigger than 1, so that's the vertical stretch. Compressed vertically, that means you have a fraction less than 1. So that would be letter G. The horizontal ones those are on the inside. A stretch horizontally means it's going to be stretch horizontally is going to be less than 1. If I look at that, the one that's less than 1 would be Q. That means a compressed vertically looks like the stretch vertical. That would be your J, which is 4/3. That's greater than 1, and 4/3 is greater than 1. Next, describe the dilation in each function as it relates to the graph of the parent function. So for this one, we're going to actually graph this one as well. So let's do the parent function first. The parent function is at 0, 1, 1, 2, 2, and so forth. So there's the parent function. This one is now saying we are going to dilate that. Since it's on the outside, this is a vertical, and it's bigger than 1, so this is a vertical stretch. It's a vertical stretch, so if I were to stretch it vertically, I would just take all of whatever my x is and then multiply it by 3. So if x was 0, 0 times 3 would be 0. If x is 1, the absolute value of 1 is 1. 1 times 3 is 3. And then -1, the absolute value of -1 is 1 times 3 is 3. And if I had 2, 2 times 3 is 6. -2, that would also be 6. So my equation would look, or my graph would look like this, which you can tell I'm stretching it vertically, which would be a more steeper line. Now you could also do this on your calculator. I went back to my y equals and clear everything. If I want to do the parent function, I just do math over, choose number 1, and then put an x. That's the parent function. And now if I do the same thing, but now do 3, math over the numbers, number 1, and put an x. Now if I graph these, I'm going to go to zoom, and I'm going to go to number 6, just standard form. There's the parent function. Here's the other one. You can see that it's stretched vertically, means I have a steeper slope. Next, reflections with absolute value functions. So again, reflections is dealing with your A, your dilations, and if there's a negative involved. So if the A is on the outside and it has a negative, well, if A has a negative, it opens upward. Or no, if A is positive, it opens upward. If it's negative, it opens downward. So that is important with that one. And going back to that one, so if A is on the outside, it's a reflection across the x-axis because your y's are now changing. Now here, if it's the A is on the inside, it's a reflection across the y-axis. And same thing, if A is positive, it opens upward. If A is negative, it opens, this should be say, downward. So the phrase that best describes how each parameter affects the graph of g of x equaling -5 times absolute value of x minus 2 plus 3 in relation to the parent function is shown. So -5 tells us it's a reflection because there's a negative. It's a stretch vertically because it's on the outside, and it's greater, the absolute value is greater than 1. It's a translation to the right because our h is 2, positive 2, and it goes up 3 because I have a positive 3 there. So we'll just skip this part here. Actually, let's go back to here. The absolute value of -2x and the absolute value of 2x, they appear to be the same. Why would it? Because whatever your y values are going to be, it's always going to be a positive y value because of the absolute value. If you were to graph it, they would look identical. But they would look very similar to them. So if we go back to this one, I put a negative 2x here. And the other one, I just did 2x. And then graph it. There's the first one. Here's the second one. Let me go back to y equals, let me get rid of this 3 here. There, and then here's the first one, and here's the second one. You'll notice you didn't see the second one because it's the exact same one. So for the absolute value, they are going to look similar with that. Now let's take a look at an example here. It says describe how the graph of each function is related to the graph of the parent function. So Q x equaling negative 3/4 times the absolute value of x. So this is on the outside, so this is a vertical. And then 3/4, this would be a compression. Negative, so this is going to reflect over, now it affects our y's, so reflected over the x-axis. And so you can see in our diagram here, you can see the original one, I flip it, it's now underneath x-axis. Next one, the numbers are on the inside, so this is a horizontal change or dilation. Absolute value of negative 4 is 4. 4 is greater than 1, so this is a horizontal compression. There is a negative involved, and because the negative is on the inside, this is reflected over the y-axis. So your y's still stay positive, but it's just reflected over the y-axis here. Next, describe how the graphs of these function changes. The g of x equaling negative 2 times the absolute value of x. So I know this is a vertical dilation because the negative 2 is on the outside. Its absolute value of negative 2 is bigger than 1 because it's 2, so that would be a vertical stretch. There's a negative, so that means we're reflecting. So reflected over, since it's on the outside, it's reflected over the x-axis. Now your y's would be negative. Next, you can use the equation of a function to understand the behavior of the function. Because the constants a, b, and k affect the function in different ways, you have to develop an accurate graph of the function. So again, here's our standard form that we're going to use for absolute value. If h is greater than 0, so h is positive, the graph moves to the right. If h is negative, it moves to the left. If k is positive, it goes up. K is negative, it goes down. So this is just a review of what we've gone through already. The reflection part, if a is greater than 0, it opens upward. If a is less than 0, it opens downward. If the absolute value of a is greater than 1, it is a stretch vertically. If a is less than 1 but greater than 0, it's a compression vertically. So now let's look at this one. It says graph p of x equaling negative absolute value of x minus 3 plus 5, and then state the domain and range. So let's graph this first. I know the absolute vertex is right here, so 3, 5. So I can go to 3, 5. That's my vertex. Then we could just choose numbers on each side of that to plug in to find our other ones. So let's just say I put in, let's just put 0 in for x. If I put 0 in for x, 0 minus 3 is negative 3. The absolute value of negative 3 is 3 times negative 1 is negative 3. 3 plus 5 is 2. So 0, 2. And then I know that I am 1, because if I had have a line of symmetry there, I can mirror this one. So this is 1, 2, 3 steps away, 1, 2, 3 steps away on the other side. But to verify, if I put 6 in for x, 6 minus 3 is 3. The absolute value of 3 is 3 times a negative 1 is negative 3. Negative 3 plus 5 is 2. So here's my graph. You'll notice that it opens downward. Why does it open downward? Because there's a negative sign in the front. Now it states the domain and range. So the domain x such that x would actually be all real numbers. So I can just say x is an element of real, or you can just say x is all real numbers. The range y is such that y is less than or equal to 5. It never goes above 5. It stays at 5 and goes below 5. Next, graph this one and then state the domain and range. So again, there's a plus k here. We don't have that there, so this is really 0. So we have 4, 0. So 4, 0, this would be our vertex here. Then from that point, we just choose points on each side of it. So let's choose a 5. If I put 5 in here, 5 minus 4 is 1. The absolute value of 1 is 1. 1 times negative 2/3 is negative 2/3. So I would have a 5 and negative 2/3, which would be roughly here. That means the other side would be roughly there. Let's try putting we put a 6 in here. 6 minus 4 is 2. 2, absolute value of 2 is 2. 2 times negative 2/3 is negative 4/3, which is negative 1 1/3. So that'd be here and that'd be here. So I roughly have what I need. Graph would be layered there. Domain. Again, the domain x such that x is going to be all real. I can put any x's in there and it will land on there. The range y such that y is less than or equal to 0. It never goes above 0. So that would be our domain and range on that. And our last question here says graph this one and then state the domain and range. So again, our vertex is at negative 7, 0. Now here I'm going to actually show you on your calculator again how you could do it on your calculator. If I go to y equals, I would have negative 2, hit the math button, go to numbers, number 1, and I would have x plus 7, end parentheses, and I'm going to get rid of this other one down here. Then if I hit graph, you can see what the graph would look like, but to plot it, hit second graph, get to tables. I need to scroll up. I know it's at negative 7, so I want to get to the negative 7 part for my x. Okay, so we have is negative 7, 0, and we have negative 8, 2. So we got negative 8, negative 2. That means we'd have negative 6, negative 2, and our graph would look like that. So then we would have our domain x such that x is all real, and the range y such that y is less than or equal to 0. Never goes above 0. So that would be our domain and range. That is our lesson today on absolute value functions.